Okay, so we will now discuss about decision trees, but we'll do it in a different context. Previously, when we discussed about decision tree construction, we had assumed that each of the samples was equally weighted. Today, we'll discuss about the case when the samples could be differently weighted, and also when the weights could be in terms of fractions and not just integers. Let us draw a really trivial example. We have real inputs, two features x1 and x2. Let's just draw the two classes, 2 plus and a minus on this side of the plane, and a plus and 2 minus on this side of the plane. Now, to make things interesting, we'll say that instead of having uniform weight for each of these samples, we'll have some different weights for these samples. Let's consider we in total we have 6 samples. Let's assume that we want the sum of the weights of individual samples to equal to 1. So we could assign a weight of 0.3, 0.3, let's say, to these 2 points, which I've done intentionally because they seem to be wrongly classified. If you were to draw a trivial decision boundary between somewhere around x1 equal to some value between these points, let's give a weight of 0.1, 0.1, 0.1, and 0.1 to the remaining 4 points. Thus, the sum of the weights is equal to 1. Now, the sum of weights equal to 1 is also a setting which is common, especially in algorithms like AdaBoost, where this is done by design. Let's now see how we can compute the entropy and find the information gain. So what this weightage basically is suggesting is that, let's just consider one particular example now. For now, let's look at this negatively highlighted sample, a negative class highlighted sample. This has a sample weight of 0.3. So this could effectively be seen as it's zero point 0.3 of a sample belonging to the negative class. Similarly, for the other samples, you could think it's 0.1 of a sample. It's not a full sample, it's a fraction of a sample. So with that background, we can now go ahead and compute the probabilities of the individual classes, plus and minus, which are required to compute the entropy. So if we write the formula for entropy of this set, that will be minus the probability of the plus class log base 2 probability of the plus class minus the probability of the negative class and log base 2 probability of the negative class. Now, the only difference between what we're studying now and what we've studied earlier is now we have weighted samples instead of unweighted samples, or where all the samples are equal weight of 1. So the difference we'll now get is that the probability of plus, for calculating the probability of plus, let's see the samples which have the plus class. These samples are 1, 2, and 3. So we have 3 samples. Their relative weights, or the weights, are 0.1 plus 0.1 plus 0.3 divided by sum of weights of all the samples, which is 1. Therefore, probability of plus is 0.5. If we do a similar calculation for probability of negative, it will turn out to be also, for the negative classes first, let's the points having negative classes. These points are 1, 2 and 3. Probability of negative is just sum of the weights divided by the total sum of weights, which is also 0.5. Thus, if we now compute the entropy, we can compute this as, I'm going to just write it over here, at the entropy is minus half log base 2 half and minus half log base 2 half, which is 1, which is the maximum possible entropy when you have just two classes. Okay, so far so good. Now let's try to see if we were to learn a decision stump on this particular set of samples with these weights. How would it look like, and how would we do the information gain formula? So I'll create a copy of this data set and let me get rid of all this stuff which is not relevant in the current discussion. Okay, so let's assume that we draw a boundary like the following. I'm going to label it as chosen split according to the information gain criteria. So what we're going to see is we're going to evaluate how good this particular split is. Let's not call it as chosen split. Let's call it a candidate split. And we want to see how good of a split is this. Now, let's first look at what happens to the left-hand side. Let's try to calculate the entropy of the left-hand side of so entropy of, let's just call the split point as x1 star. Entropy of the set x1 less than equal to x1 star, which we can also mildly, just to ensure that all of us are on the same page, we can also highlight it as this particular region. And if you're trying to find out the entropy of this particular region, it has probability of plus being 0.1 plus 0.1 divided by 0.1 plus 0.1 plus 0.3, which is 0.2 by 0.5. Probability of minus is 0.3 divided by 0.5. So thus, using this formula or using this weighted probability of plus and minus, we can calculate some entropy of this subset of examples. We can repeat the same procedure for the second subset, which is the second subset is, and this particular point was, let's say, x1 star. So if you want to calculate the entropy of the region x1 greater than x1 star, which we can also highlight using, let's say, some other color. Okay, so for this particular region, we have probability of plus being 0.3 by 0.5, probability of negative class being 0.2 divided by 0.5. So using this particular split, we can now calculate the entropy of the right hand side also, and we have thus far calculated the entropy of the left hand side also. Let's go back and say that for now let's just call it E1. Let's go back and say the entropy of the entire set is E, or let's call it the entropy over the set of samples S, and let's call this quantity of E of the samples where x1 less than equal to x1 star, and let's call this quantity as entropy of the set of samples S where x1 greater than x1 star. Now the only thing we are left to do is to calculate the information gain for this particular split of x1 equal to x1 star. So we want to calculate information gain for the split x1 equal to x1 star. So this is going to be entropy of the set of samples S minus the weights of the samples which are on the left hand side, and that is going to be multiplied by the reduced set of samples x1 less than x1 star. This whole term is going to be weighed by the set of the sum of the weights, which is 0.5, plus the sum of the weights for the entire set, which is on the left hand side the sum is 1, on the right hand side the sum is 1. Similarly, we compute this as the next term as weight is 0.5 divided by 1 times the entropy of the set where x1 is, let's say, greater than equal to x1 star. So using this formula, we can now calculate the information gain for this particular split. We could have also chosen some other split and obtain a similar solution.